Welcome. Thank you for joining us for today's webinar, Advanced Passive Thermal Management, Applications and Solutions, presented by Advanced Cooling Technologies and TechBriefs Media. I'm Bruce Bennett, editor at TechBriefs Media, and I'll be your moderator today. This webinar will last approximately 30 minutes, and there will be a question and answer period at the end of the presentation. If you have a question, you may submit it at any time during the presentation by using the Ask a Question box on your screen. Our speaker will answer as many questions as possible at the conclusion of the presentation. Those questions not addressed during the live event will be answered offline. To view the presentation properly, please disable any pop-up blockers you may have on your browser. At this time, I'd like to introduce today's speakers, Denis Pamukchu and Taylor Maxwell. Denis Pamukchu joined ACT in 2014 as a product design engineer in the Custom Products Group. Denis has served as the technical lead on a variety of programs, successfully providing thermal management solutions to a variety of commercial customers. Currently, Denis is responsible for new business development in the northeastern U.S. territory. Denis holds Bachelor of Science degrees in Chemical Engineering and Business Management and a Master's of Engineering and Technical Entrepreneurship from Lehigh University. Taylor Maxwell is a product development engineer in the Custom Products Group. He works directly with customers to conceptualize, design, and analyze thermal solutions for electronics, medical, temperature calibration, LED, and other technical markets. With 3 years of experience in the Custom Products Group and 2 years of experience in the Defense and Aerospace R&D Group, Taylor has cultivated a broad technical background and gained hands-on project management experience on a variety of different programs. He received his BS and MS in Mechanical Engineering from the University of North Florida. Now that you're familiar with our speaker's qualifications, let's begin today's presentation.
Thanks, Bruce. This is Denis speaking. We're going to talk about advanced passive thermal management solutions as part of this webinar. So with me is Taylor Maxwell, Product Development Engineer. This presentation will begin with an overview of what is a passive thermal management solution. We're going to talk about some of the benefits of these applications, using passive thermal management in these applications, and finally we'll discuss some of the tools used in passive thermal management solutions, including heat pipes, high-K technology, and loop thermosiphons. So what is passive thermal management? In most terrestrial systems today, conduction and convection are the primary modes of heat transfer. Thermal solutions in which no additional energy is used by the system to reject the heat are classified as passive. As an example of some active elements in solutions, thermoelectric coolers, fluid pumps, and fans are all considered active elements as they are powered. Let's now talk about some of the benefits of passive thermal management solutions. The first, and this is fairly obvious, but is energy consumption. The less devices you actually have wired as part of your system, the less electrical power is necessary to power it. This can benefit you in a few different ways, including if it's a portable application using a battery, the less of that solution that's actually tied into power, the less battery power you're going to need, and the more battery life you'll provide for your customer. The next would be complexity. Passive solutions tend to be less complicated due to the fact that they involve less plumbing and or wiring. Reliability is increased in passive thermal management solutions due to the lack of fluid connections and or electrical connections and moving parts as well. Moving parts will decrease the mean time before failure for those components and impact your overall system mean time before failure, and fluid adds the risk of fluid leaks. Weight is also impacted by moving to a passive thermal management solution. In applications that require pumps, those pumps are generally heavy. So by removing those pumps from the system and designing in a way that you don't need them, you can impact the weight and hopefully reduce the weight of that system. So what are some of the common reasons for moving to a passive design in your thermal solution? One would be to remove the recirculating liquid chiller. we here at ACT work with a lot of customers, and we've seen that in the medical and industrial industries, separating the product from this chiller is something that's desired. Passive designs allow you to accomplish this. Another application would be in the design of RF and/or airtight enclosures. In some of these applications used in defense and aerospace industries, it's not possible to run a fan and/or a liquid loop inside the enclosure due to the impacts it has on the performance. In these applications, some of the passive technologies we're going to talk about can be implemented. Another area in which passive design is desirable is where noise and vibration are undesirable. We've seen this utilized in a lot of laser systems and/or optical type devices where a pump or fan may transmit vibrations that can negatively impact the end application. And finally, passive solutions are a great fit for ruggedized designs where lowering the amount of moving parts or minimizing the amount of moving parts inside that device increases the mean time before failure, overall providing a more ruggedized product. So now that we've talked about some of the common reasons for passive design and described what is passive thermal management, we'd like to talk about some of the tools that you can apply to these systems, the first being heat pipes. We here at ACT design a variety and manufacture a variety of heat pipes. Today we're going to be talking about copper water heat pipes. A heat pipe is made of three main components, including the envelope material, which in the copper water case is the copper, a wick structure, which is a sintered copper on the inner diameter of that copper envelope, and a working fluid, which in the copper water case is the water part. A heat pipe is essentially a sealed copper tube with that working fluid on the inside. We pull a vacuum on the device, meaning that it's operating along that working fluid saturation curve. Heat input into the heat pipe in one location causes that working fluid to vaporize, travel axially down the pipe, and then condense into the pipe wall in a cooler location, letting off its heat. That fluid is then pumped via that wick structure back to your evaporator. This is a completely passive solution that requires no additional energy input, yet moves a tremendous amount of heat from one location to another. A properly designed heat pipe will have about a 2 to 5 degree delta T across the length of this heat pipe and has extremely low thermal resistance. What do you need to know to design a heat pipe? Well, one of the first things to consider is the amount of power that you're going to need that heat pipe to carry. The heat sink and heat source parameters are also critical to understand where that heat pipe is actually going to operate. The operating temperature of a heat pipe is one of the factors that dictates how much power it can carry. Understanding the temperature range across which you need that heat pipe to operate is also critical. If you're operating your device higher than 150, 200 C, you may need to look into a different type of heat pipe. Non-operational temperature range is also critical, as the storage requirements for that heat pipe will dictate some of the material and fluid compatibility. So after you understand the inputs into your heat pipe, you want to understand what type of heat pipe will carry that power for you in that environment. For this, ACT offers a free online tool to help you in your initial sizing. This tool allows you to input 4 variables, including the heat pipe length, the evaporator length on that heat pipe, the condenser length on that heat pipe, and the height against or with gravity which it's operating. When your heat source is lower in plane than your heat sink, that heat pipe is operating gravity aided. Reversing that, the heat pipe will operate against gravity. In the image on the right side of this slide, we are depicting a heat pipe application where the heat source contacts about 1 1/4 inches of the heat pipe, the heat sink contacts about 2 inches of the heat pipe, and the total transport distance is 4 inches, gravity aided. If we need to move about 70 watts of waste heat, and we know the chip should operate between 60 and 70 C, how do we know which diameter heat pipe will work? Well, if you input those variables as you see in the bottom right of this slide and click Submit, what you'll be presented with is a graph similar to that on the right side of this chart. The operating point is the 70 watts, which is shown on the y-axis of the chart, and the black line indicates that point. Knowing that we have to operate the heat pipe somewhere between 60 and 70 degrees C, we can draw that yellow bar across the chart. The intersection of the yellow bar and the horizontal black line shows us the operating point that we desire for that heat pipe. This chart shows you that you're going to need at least a 6 millimeter or potentially a 1/4 inch heat pipe to move that 70 watts from your heat source to your sink given those operating conditions. And or another way to look at this chart is that you can use potentially 2 8-inch heat pipes to move about 35 watts each, totaling that 70 watts. So you've determined how much power you need to move, and now you understand what type of diameter heat pipe you need. Next, let's talk about how you can design that heat pipe into your next level assembly. Heat pipes can be bent and flattened, which aids in their ability to fit within your application. We recommend a minimum bend radius of 3 times the outer diameter of the heat pipe. For instance, in our past application, or past example, where you had a 6 millimeter OD heat pipe, we would recommend a minimum bend radius of 18 millimeters. A heat pipe can also be flattened. ACT recommends flattening a heat pipe no more than 2/3 of its OD, i.e., for a 6 millimeter heat pipe, you'd like to flatten that to no less than 4 millimeters. ACT uses standard pipe sizes to generate heat pipes, meaning that any pipe size from a 3 millimeter to a 1-inch diameter can be used to create a functioning heat pipe. That heat pipe is traditionally attached to either your evaporator or your condenser via epoxies or solders. So now that you've designed the heat pipe, both mechanically and understood that it can carry the amount of power you're looking for, you're going to integrate that heat pipe into your model and do some modeling to find out how it performs. To do this, ACT has some first-order modeling guidelines that you can follow. Take that heat pipe, embed it into your mechanical design as a solid element, and apply to it a starting conductivity of about 10,000 watt per meter K. For reference, aluminum is about 200 and copper is about 400. Run your simulation and check the maximum temperatures across that heat pipe element. A properly designed heat pipe that can carry the amount of power will have a 2 to 5 degree delta T across its element. If you run your model and you find that your heat pipe has a 5 or greater delta across it, increase that conductivity value until you meet these numbers. That would give you a good first-order approximation of what the heat pipe will do for you in your system. Finally, some time to discuss some best practices as it relates to heat pipes. Generally, in a heat pipe application, the heat pipe is a super low thermal resistance within your resistance network from your chip to your ultimate heat sink. There have been times in which customers have thought that their heat pipe is defective or the heat pipe is not working. Upon further examination, ACT has concluded that in most of these scenarios, it wasn't the heat pipe that wasn't working, rather the interface, or i.e. getting the heat into the heat pipe and moving the heat out of the heat pipe, were the primary causes of that heat pipe system looking like it wasn't properly functioning. If the resistance on one side or the other of the heat pipe is exceedingly large due to improper integration and or an air gap or something of that nature, it may look like that heat pipe isn't working. So our best practice is to take some time, think about the way that you're going to integrate that heat pipe into your condenser and into your evaporator. At this time, I'd like to throw it to Bruce for a question.
Yes, we have the first of our poll questions today. When looking for thermal management solutions, what is the single most important criteria your company uses to decide? A, cost, B, performance, or C, reliability? Please take a moment to give us your answers. Thank you, and now back to the presentation.
So now that we've talked about, I want to talk about the next logical step, which is taking that heat pipe and embedding it into your conduction plates and next level solution. Heat pipes embedded into cold plates are referred to here at ACT as high K plates. This is where we take a traditional aluminum plate with a conductivity of about 200 watt per meter K, and we embed into it a heat pipe in a way that increases its thermal conductivity anywhere from 500 to 1200 watt per meter K. That range is so large due to the length of the heat pipe that potentially is inserted into that plate. The longer the heat pipe, the higher the effective conductivity is going to be within your plate. The benefit here is that you now have a plate made of aluminum embedded with heat pipes that still has the same weight of aluminum, the same structural strength as aluminum, but an exceedingly high thermal conductivity. As you can see in this example, where the customer has both an aluminum plate and a high K plate in the same design, the maximum temperature on the aluminum plate is around 90 degrees C, whereas the maximum temperature on the high K version of this plate is around 60 degrees C. This is achieved because the heat pipes are passively transporting that heat and spreading it throughout that plate, taking better advantage of all the mass available. Additionally, in this application, that plate was locked into a liquid-cooled chassis as denoted by the solid blue lines. Spreading that heat more evenly into this liquid rail reduces the flux and also increases the efficiency of the system. This type of solution is considered passive because this could have been accomplished by running a serpentine channel underneath that plate and pumping fluid directly into the plate. However, that would have increased the weight of the system and also added potential leak points. So in this application, the high K technology is more passive solution, a more reliable solution than potentially turning this plate into a liquid cold plate. Next, let's look at a high K heat sink case study. This application, ACT took an aluminum extrusion of a given base thickness and footprint and applied in the center of it a 150 watt thermal load. ACT then designed an equivalent performance heat sink that has a much smaller footprint and overall reduced mass by 34%, but with the embedded heat pipes. As you can see on this next slide, these two heat sinks have equivalent thermal performance when that 150 watt load is applied, although the heat sink on the right, the high K heat sink, is 34% less in mass. Another brief case study is taking a chassis wall, which is liquid cooled on the bottom, and applying to it an embedded heat pipe plate to spread heat from that chassis wall and the cards down into that liquid rail. As you can see on the left side of this image, when that plate had no heat pipes and was only a conduction-based solution, it had these hot spots occurring near the top of the card. By adding an embedded heat pipe solution to the reverse side of that card, ACT was able to decrease the temperatures seen across that card by 20 to 30 degrees with no change to the legacy chassis or pumped liquid loop. And finally, we talked about frames, we talked about chassis walls, and we talked about heat sinks. Now we'd like to talk about the cards themselves that are put into these chassis. ACT has also worked on these card frames to turn them into high K type solutions. By embedding heat pipes into the cards themselves, the components that are on those cards are directly in contact with the heat pipe, and the heat pipe transfers that heat out to the edges, where it then can be integrated into chassis and rejected from the system by air or liquid. This is, again, a passive solution because the alternative here would be to potentially put fans within the chassis itself and or pump liquid directly into the chassis, which again provides more complicated assembly as well as adds leak points that will decrease the mean time before failure. This next slide shows an example of these high-K card frames. Again, by embedding heat pipes into that aluminum conduction card, ACT is able to reduce the maximum temperature seen by those components by 20 to 30 degrees C by adding no moving elements and no additional energy cost. A good first-order modeling assumption that can be made that you can make in your system today to see if a high-K solution might benefit your ultimate application is to take those aluminum conduction plates that are currently within your system, any heat spreader that is made of aluminum, and change its material properties from 200 watt per meter K conductivity to a 600 watt per meter K thermal conductivity. If this makes an impact, a positive impact on your application, it's something that can be readily achieved by high-K technology. At this point, I'd like to turn it back to Bruce for another polling question.
Thank you, Dennis. Our second polling question involves need. Do you have a current need for thermal management solutions? A, yes, we have a need now. B, foresee needing them in the next 0 to 6 months. C, foresee needing them in the next 6 to 12 months. Or D, no current or foreseeable need. Please take a moment to give us your answers. Thank you. Now we'll go back to the presentation.
So we talked about heat pipes and high-K plates, which are great for tens and hundreds of watts worth of thermal transport in a passive way. However, what if you want to transport kilowatts worth of power and do that passively? For this, we're going to talk about loop thermosiphons. A loop thermosiphon is a passive two-phase cooling solution that relies on a gravity head to pump liquid from your evaporator to your condenser. What do we mean by that? Well, on the image on the right-hand side, you see a traditional thermosiphon. A traditional thermosiphon resembles a heat pipe, except without a wick structure on the inside. Heat input causes a vapor to form and travel up the pipe where it's condensed and then flows back down to your evaporative region where the process will repeat. In a loop thermosiphon, the image on the right, your vapor and condensate flows are separated. This allows for higher performance in this device, while again maintaining a completely passive operation. How do you implement this technology? Well, a loop thermosiphon consists of 4 main components: an evaporator body, a condenser, a liquid line, and a vapor line. The heat generating components that you want to cool are mounted to your evaporator body. The heat generating components will cause the liquid within that evaporator body to vaporize, travel upwards into the air-cooled condenser, where the heat is given off to the air, the vapor is turned back into a liquid, and will rejoin that liquid pump head. In most of these applications, the condenser is air-cooled. However, we here at ACT think of this as an advanced passive thermal solution due to the concentration of that heat and the concentration of all your fan power. Having these fan power, having the heat sinks for these components distributed throughout a system will add more points of failure. In this way, by concentrating them into a single device, you're making use of this advanced passive transport to condense the back end of the solution. Loop thermosiphons can be implemented in a variety of ways depending on the packaging constraints and the airflow that's available. On the right-hand side of this image, we show a variety of different designs that ACT has made. These designs show IGBTs mounted to your evaporator plate, as this product was initially designed for the power electronics market. The only main rule in designing a loop thermosiphon is that your evaporator must be lower with respect to gravity than the condenser. This enables the liquid head to form and passively pump your fluid through your evaporator into your condenser and have that cycle repeat. The evaporator design is also variable and not restricted to a plate form factor. Devices placed on one side and or both sides will operate in the same exact way. Looking at the performance of these devices, ACT, again, generated the initial product offering for the power electronics market and has shown over 10 kilowatt worth of heat dissipation with a very low 0.005 degrees C per watt thermal resistance. As you can see on the chart on the left-hand side of this slide, your average cold plate temperature will increase with the amount of power transport through the system. For instance, if you're trying to move about 8,000 watts, we found that we can maintain a cold plate temperature of somewhere near 60 degrees C. And that will drop as you lower the amount of power carried by the system. Another benefit to using a loop thermosiphon is that due to the vaporization happening within that evaporator plate, the temperature of that evaporator plate is held relatively constant from end to end. In a typical pumped liquid system, you'd anticipate quite a temperature rise from end to end with a heat input of 7 kilowatts. However, across this plate, due to the two-phase operation, we see only about an 8 degrees Celsius spread. Loop thermosiphons are excellent devices to transfer kilowatt-level thermal loads with very low thermal resistance in your applications. At this point, we've talked about heat pipes, high-K technology, and loop thermosiphons, all of which are passive or semi-passive advanced solutions for heat transport in your systems. The benefit of passive thermal operation can be in energy consumption, increased reliability, decreased complexity and weight, and reduction of noise and vibration which may be caused by pumps and fans. We hope you enjoyed and learned something from today's presentation. And at this point, I'd like to thank you for your time and take any questions that you might have.
Thank you, Dennis, for that most informative presentation. Now, as you noted, let's take some questions from the audience. First question, what is the difference between the methods used to attach heat pipes?
Right, so for most copper water heat pipe applications, typically using solder, alloy, or thermal epoxy is the most common way for attaching heat pipes. For higher heat flux applications, solder is usually more preferable due to its higher thermal conductivity, whereas thermal epoxy is slightly lower in thermal conductivity, but can sometimes offer a more cost-effective solution.
Thank you. Next question. What kinds of working fluids are used in a loop thermosiphon?
For a loop thermosiphon, we typically use dielectric fluids such as refrigerants like R134A, mainly because of their high liquid to vapor density ratio. Also, using dielectric fluids for electronics cooling applications is advantageous in the rare instance that you have a leak. The dielectric fluid will not short out electrical components nearby.
Thank you. What limits how much power a loop thermosiphon can handle?
The power capability of a loop thermosiphon is dictated mainly by the amount of flow that can go through the system. Because the system is, the flow is gravity aided, the larger the difference between the evaporator and the condenser in terms of overall height, the more flow and pressure head can be generated, and this will result in larger powers being able to be dissipated.
Thank you. Here's a good one. You mentioned water within a copper tube. Can heat pipes survive freezing temperatures?
Yes, specifically water heat pipes that can survive freezing temperatures. What we typically do is charge the heat pipes so that the wick is fully saturated, but there's no excess working fluid that can pool up and bridge the diameter of the heat pipe, resulting in a bulge during freezing. So by properly charging the working fluid, we can avoid freezing even in water heat pipes.
Thank you. What distance can a heat pipe transport heat against gravity?
The distance that a heat pipe can transport heat against gravity is dependent on several variables, mainly the outer diameter. Typically, the larger the outer diameter, the more power can be transferred against gravity. Also, the type of working fluid that's used and the surface tension associated with that working fluid. So the higher the surface tension, the better that working fluid can climb against gravity in the wick structure, resulting in an overall greater heat transport capability.
Thank you, Taylor. I'm afraid that's all the time we have. I'd like to thank Dennis Pamukchu and Taylor Maxwell for giving us such an informative presentation. And I'd like to thank today's attendees for participating. That concludes today's webinar sponsored by ACT and TechBriefs Media.